Fire can transform matter into things of beauty and use. Or it can become the destroyer of worlds. Alright, today I'm going to do a tutorial on glaze and what it is, because I was having trouble finding one that was showing the sort of thing that I wanted to show my students. So this is an example of a glazed piece of pottery. This is stoneware. The bottom isn't glazed because glaze is glass. It turns into glass when it melts, and then when it re-solidifies and freezes, it turns into glass, and it would stick to the kiln shelf if you put glaze on the bottom. So there's one piece of pottery. The best place to start is with the basic materials that make up a glaze. These are different types of rock or shale, and they're clay-like shales because all of these would dissolve in water. This one is a crumbly material that has a pretty good amount of iron in it. This has a lot of iron. This has iron. Iron most often produces a color like this, rust, because that's what it is. And in the case of this particular one, it's green, I believe, because it didn't get oxygen when the iron was put into the clay. When the clay formed, there wasn't oxygen available to cause the iron to turn into iron oxide. Here are most of the basic ingredients in glaze in this gravel. If I pick through here, that looks like a piece of quartz. This is a piece of feldspar. Pretty sure I saw a piece of, here's a little piece of limestone, I think. But the idea is that the basic ingredients in a glaze come from ground rocks and just plain soil, which this one may be a prehistoric soil. This would probably melt at some temperature and produce a brown glaze. The main components of a glaze are silica, which is ground quartz sand. It's the glass former. Alumina, which is the oxide of aluminum. This is the oxide of silicon. And flux. Alumina helps stabilize the glaze and harden it because you need to lower the melting temperature of glass, of the silica. Silica melts like over 3,000 degrees, and it takes a really expensive kiln to fire things to that temperature. So you try to bring the temperature down with the flux, which is the melting agent, lowers the melting temperature of the glass. And sometimes the glaze melts, but it wants to run. You can use a hardener or a stabilizer, which is alumina, to make the glaze to affect it so it either runs more or less. You can bring it back and forth. You can also adjust how much it melts or doesn't melt by the amount of the melting agent, but you change these two in proportion to this one, the glass former, to get the glaze to fit your pot and your firing temperature. Another way to look at this and this is chemistry. This is the way I learned a long time ago. RO2 is your glass former, R2, O3 is your hardener, and RO or R2O are your oxides of things like potassium, magnesium, sodium, nickel, and these cause this to melt. So that's just two different ways to look at it. This is flint. I think I had this written down here, yeah. All right, let me go back. I made a mistake. This is flint, sand, or quartz. It's ground quartz, silicon with an oxygen, so silicon dioxide. And this is the glass former. Sometimes to lower the melting temperature, they make special compounds that usually include borates. They fight, and borate is not a nice material to work with usually. Like borax can make a glaze melt, but it's got properties that make it difficult to use. So they fire borate compounds that are kind of like the feldspar, and they fire them until they melt, and then they grind them finely, and you use a powder of frit to replace some of the feldspar or some other agent that has a flux in it. And kaolin is basic clay, and kaolin has a water molecule. Many of these compounds have something that they call loss on ignition. When you fire them, certain things disappear and they're gone. Water goes right up the chimney in the case of this one. Books on the subject. This is an old chemistry book that I have, an elements book that I like quite a bit. It went through a house fire, so it's got carbon on the cover. But this book has a periodic table in it. You can get as deep into glaze chemistry as you want. You can figure out the molecular weight of any compound by counting the numbers of each atoms and picking them out of the table and adding the numbers up to get the molecular weight, which is what you use if you're trying to calculate a glaze. I'm not really going to talk too much about that. I want it evident that here's one coloring agent, copper, and there's a couple pages in this book on it. I only need a little bit of the information out of this book to know about copper to be able to use it in a glaze. You should also have some sort of a book when you're working with glazes with tables in it of materials and compounds. This is a back of this book is full of recipes, but there's pages here that show you the temperature. That's a conversion between Celsius and Fahrenheit. There are tables that will give you the molecular weight and the makeup. Over here on this side, the makeup of certain compounds that you use in glaze, so you can figure out how much flux you're putting in and how much hardener and how much glass. That was an old book by Daniel Rhodes, but this one I just picked up this morning is a more modern book, which is more like what, if you went to buy one, you would probably get one like this. This one's by Brian Taylor and Kate Duty. This book has the things in it that you need. One, here's pages showing samples and how to make samples. I saw some, here's a periodic table some coloring agents, pictures of different metal oxides that you would use to color the glaze. There are the same types of information in this book as the other book that I just had, but this one has glazes and nice pictures of different people's pottery and what they did with the glazes. So, being the way things have changed, I suppose I'd recommend a book like this, but a book like the one that, if you really get into glazing, one of the older books would have the same information, it just wouldn't have the pictures in it. Okay, so different types of glaze. I showed you one earlier of a cone 6 stoneware. This is a mortar for a mortar and pestle that I made, and the glaze on this is actually this green rock ground and mixed with flux to lower the melting temperature, because this will turn into a glaze at like 2300 by itself, but I only fired to like 1865 with the pottery redo. And this actually I took up to cone 3. I don't remember, that's somewhere around 2000 or a little more. It's getting close to stoneware, but not quite. It wasn't a high enough temperature to fuse the clay, so when I grind in this mortar, dust comes out of it. I need to try and get it up to cone 6, which would likely fuse the clay enough that I could use it as a mortar. But the key here is this is a beautiful glaze, and it's mostly just this green rock ground. Here's some more examples that I melted at the lower temperature, the 1860, whatever it is, 65, 68, something like that. And I added different amounts of flux to it, but I had to add so much that it started to lighten it up, and it started losing its nice green color. Here's some more low temperature glaze samples, examples of them. These are made by doing tests. You make 100-gram batches using a triple beam scale, and the recipes are in percents, and so you put in, when you get done, you have a 100-gram batch. That way it's easy to tell how many percent of each thing you added to the glaze. And then on top of that, you add coloring agents. And in this case, this one was chromium, probably something in the half to 1.5, 2%. Sometimes you go higher with some coloring agents. This is a cobalt carbonate, which is it turns into an oxide after it's fired. This one I believe was rutile. This is copper in the presence of sodium. That's where that blue-green color comes from. These two were attempts to make chrome tin pink. We got a pink color, but you can get a pretty nice magenta or maroon color with chrome tin, particularly at cone 6, which is quite a bit higher. Cone 6 is like 1,150. I mean 2,150 degrees, and it is stoneware at that temperature. It's on the low end. These are bisque temperature because they're still pink, and as opposed to this clay was fired to stoneware. I believe this is a cone 6, and if you put moisture on it, the moisture will not soak right in. If you put moisture on this, it'll soak in. I much prefer to fire to a higher temperature, but I can't with the kilns that I have at my school. So, alright, the last thing I want to talk about is the business of the coloring agents. This is copper oxide, and copper can be a carbonate. There's a couple forms of oxide. This produces a nice jade green color, We have chromium oxide, which produces a green color that's more like algae or something like that. I'll put a little tiny bit because this one, even when it's not fired, is pretty bright. And it is one of the colors that comes out similar after it's fired. Many colors don't look anything like this. Here comes out a nice jade green, but it's actually black powder. This is cobalt carbonate, which produces blue. Now, on this piece that I have right here, this orange color was produced by rutile. The white was probably produced using either zirconium oxide, or titanium oxide. Cobalt is the blue. There's some purple in here, which I believe in that particular case I got it by using chrome tin pink and cobalt, a compound of those two to make a purple. This is a chrome tin pink. The red color in there is chrome tin pink. The blue-green color, I believe, is most likely chromium and cobalt. Makes a color like that. You can get a turquoise-like color from a mixture of chromium and cobalt. The lighter green is a copper type green. This pot has a different look to the surface. It's more of a matte surface. This has some lavender color, which came from a manganese purple. I don't remember exactly how I got this, but I'm fairly certain this one was a purple that I got from manganese. It's not a real overpowering purple, but it's a real nice purple. There's some cobalt on there. There's some copper green glaze on there. So by using these oxides to put a colorant into the melted glaze, you can change the color. All the examples I have here are fired in a normal electric kiln, which has that oxidation atmosphere, and you're not putting carbon in there. But if you use fuel and pump carbon in the kiln and have it combust, you can remove oxygen and make the fire starved for oxygen, and it'll produce excess carbon. And if you have a pottery fired in a reduction atmosphere, which is what happens when you have a lot of carbon, it'll change the way the oxides, some of the oxides will start to turn into metals, and like copper, instead of being green, sometimes it'll come out red. Iron can go red or green depending on the atmosphere. A lot of the oxides are affected by the atmosphere of the kiln. Let's see. So the basic review of it is that glazes are basically made out of a glass former, which is ground sand or ground quartz, a hardener or stabilizer, which is usually alumina. However, like I said, sometimes boron takes on the form that which is R2O3. The hardener has a form like that. There's other things that go into a glaze that have that form other than alumina, but that's the main one. And then you have flux, which are the chemicals that you add to make the glaze melt. One easy way to get a glaze on a piece of pottery, while we're thinking about flux, is just to take pottery and put it in a kiln, and if you get it to a high enough temperature, over 2000, up in the stoneware range, if you dump just plain table salt, sodium chloride into the kiln. The kiln will dissociate the sodium from the chloride, from the chlorine, and the chlorine will go up the chimney as a gas, and the sodium will attach itself to the silicates in the clay and cause a surface melting. So you get a buildup of sodium glass on the surface because of the interaction between the sodium gas in the kiln and the surface of the pot, which has a lot of silica in it. So that's an interesting way to get a glaze, just by dumping salt. But you can't put salt in a glaze because, again, salt is soluble, and it's difficult to work with glazes that have soluble things. That's why borax doesn't work, and you have to come up with some other sort of chemical that has borate in it. There's a natural one called Gersley borate, but to get a really high borate level, usually they have to turn it into a frit, which, as I said before, is a glass that they add the chemicals to, dry, melt it, and turn it into a glass, and then they grind the glass back down into a powder, and that way it's stable because then the borate is already fused to the silica and the alumina and the other things that are in the mix. All right, I know this will help for me to be able to show my students. I hope if anybody has questions or wants to see any other thing about making glazes, like actually weighing them out with the scale, that's something I might do in a later one. I just wanted to have this information so I could give it to my students.